am sharing my screen. Okay. Today I will discuss about this CMOS logic families. Okay, CMOS logic circuits. Okay, CMOS logic circuits we will discuss. Okay, is my screen is visible now? Just to give response so that I will move forward. Yes. Hello. Hello.
Sir, can you repeat again? I am unable to hear anything.
Your voice is low. Please respond.
Cannot hear anything, sir.
You can't see my screen.
Hello?
You can see my
Yeah,
screen.
sir, it's visible. It's
Okay.
visible.
Okay. 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 Thank you. Okay. So today we'll see the CMOS logic circuits. One second. CMOS logic circuits. Okay. You already seen that CMOS is a combination of what PMOS and PMOS as pull up and NMOS as pull down. No? NMOS as pull down. Okay. So that means we already seen the ideal characteristics of this NMOS and PMOS. So if you see the NMOS, so NMOS will be, this is a symbol for NMOS. So you have gate and next drain and source. Okay. So if g equal to 0, so it will be what, off, no, ideal characteristics, so ideal devices. Okay, so drain to source, as it is acting as open circuit. Okay, and when if g equal to 1, if g equal to 1, it will be like on switch, it is acting as a on switch. And drain to source, it is acting as a short circuit. Okay, short circuit. And PMOS, if you see the PMOS, so PMOS, this is the symbol for PMOS. So for PMOS you have, this one is source and this one is drain, source and drain, and this one is gate. Okay, for the PMOS, if gate equal to 0, so this will be act as on switch. So source to drain, it is acting as a short circuit.
Gotcha.
Okay, and if gate equal to 1, it is acting like a off. Okay, source to drain, it is acting
Open
as
circuit.
open circuit. Okay, these are the ideal cases we already seen. Okay, so basically the CMOS circuit, if you see the CMOS circuit, the CMOS circuit will be any CMOS circuit will be look like this. Okay, so it will be like you have VDD. Okay, VDD, and here you have a pull-up network. Pull-up network as PMOS. Pull-up network as PMOS, and next you have pull-down network. Okay, pull-down network. Pull-down network as NMOS. Pull-down network as NMOS, and some couple of inputs will be there. Okay, so let us take this is input. Okay, you are giving. Okay, this is also input, you are giving the input. Okay, and from here you are taking the output. From here you are taking the output, and this is ground. This is the ground. Okay, this is a basic. So that means PMOS. Okay, PMOS transistor can easily pass logic high. PMOS transistor can easily pass logic high. Okay, logic high. And NMOS transistor, so NMOS transistor can easily pass logic low. Okay, so from here you can say that so if you see the logic circuit, for logic circuit, for logic circuit. So this is AND. This is nothing but what? And this one is nothing but OR. This one is nothing but OR. Okay. So for AND operation, okay, for AND operation, here PMOS will be parallel. PMOS will be parallel, and NMOS will be series. PMOS will be parallel and NMOS will be series. Okay. For OR operation, okay, for OR operation, just vice versa. That means PMOS will be series, PMOS will be series, and NMOS will be parallel. This you need to remember. Okay. For AND operation, PMOS will be parallel and NMOS will be series. For OR operation, PMOS will be series and NMOS will be parallel. Okay. So we will try to design this first basic universal gates. So what are the universal gates? We already seen in the digital. NAND and NOR are nothing but universal gates, no? So I will try to try to design the CMOS NOR gate and next CMOS NAND gate. Okay, CMOS NOR gate and CMOS NAND gate. Okay, yeah. See design of CMOS NOR gate. CMOS NOR gate. Okay, so design of CMOS NOR gate. Okay, so first write the Boolean equation. Okay, what is the Boolean equation? Boolean equation y equal to what? ARB whole bar. Okay, this is the Boolean equation. Okay, and symbol. What is the symbol for this? So this is the symbol. This is the logic symbol for NOR gate. So A, B, and this is Y. Okay, and truth table. So truth table. So just opposite of AND gate, no? So A, B, and output Y. So 0 0 0 1 1 0 1 1. Okay. So if any one of the input is high, the output is low, and both inputs are low, the output is high. Okay. So this is truth table. Okay. For OR operation, for OR operation, we already seen what is the OR operation. NMOS will be parallel. NMOS will be parallel, and PMOS will be series. NMOS will be parallel and PMOS will be series. Okay. Yes. So here, so how my network will look like? So that means so this is VDD, and this is pull-up network. Pull-up network as a PMOS, and pull-down network. So pull-down network as NMOS. Some inputs are given. Okay, for this some inputs are given. Okay, inputs, and you are taking the output from here. Okay, so here what happens? So that means for OR operation, NMOS will be parallel and PMOS will be series, no? So just I am drawing this circuit. Okay, so here this is VDD, and PMOS. This is PMOS, and next here you have two PMOS are said to be in series. Okay, PMOS is in series. Okay, so let us take these inputs are what? A and B, and so and here this one is parallel. This one is parallel. So this you take as A and B, and here this one is connected to ground. And you are taking the output from here. Okay, output from here. Okay, so that means if you draw the truth table, so what are the inputs? Inputs are A, B. Okay, A, B, and here let us take this is what this is source, next drain, again source, drain. This is what this is anyway, these two are drains, drains, and these two are source. These source are connected to ground, and here this source is connected to VDD. Okay, so here if you see PMOS. So what is the PMOS? Let us take Q1, Q2 for PMOS. Okay, and next Q3, Q4 for NMOS. Okay, so Q1, Q1, Q3, Q1, Q2 for PMOS, and so and next Q1, Q2, NMOS, NMOS, Q3, Q4. Okay, Q3, Q4, and
Sir,
output Y. Yes, yes, tell me.
so for NMOS you have put bubbles in A and B.
Oh, sorry, sorry. NMOS no bubbles. Okay. Yeah. Thank you. NMOS no bubbles. Okay. Okay. Yes. Now tell me here. This is the output. This is the output Y. Okay. So 0 0 0 1 1 0 1 1. Okay. So here so when it is 0 0, Q1 Q2 will be what? On, no? And this will be off. This will be off. Okay, so these both are on and this will be off means what? These both are on means you are getting the output. VDD is connected to the output, so output you are getting 1. Okay, and here 0 1 means what? So Q1 will be on and Q2 will be off. Okay, Q2 will be off, and so this one is what? This one is off, and this one is on. Okay, so shall I draw and explain, or here you can you understand here? Shall I draw and explain the operation? Yes.
Yes, sir.
Okay, see here. Yeah, so here if you see, okay, I'm seeing this one. So first case, what is the first case? Here when both are like 0 0. Okay, 0 0 means here both will be on, no? So these both are short circuit. Okay, this is VDD. Okay, this is VDD, and both will be on, and here the circuit will look like this. This will be off. Okay, this will be off. Okay, and here this is ground.
From
Ground. So here what happens? The output. There is a path between VDD to output. So that means output equal to what? VDD. So
or
output equal to VDD equal to what? 1, no? In digital. Anything
yes,
is
sir.
VDD is digital. Anything
One.
is VDD is 1. Okay. And next 0 1 case we will see. 0 1 case. So this is case 1. And case 2 you see. So case 2. Uh, so Q1 will be, so this is VDD. This is VDD. Q1 will be what? On,
On.
and Q2 will be
Off.
off, and here Q3 will be off.
Off.
Okay, Q3 will be off, and Q4 will be on.
On.
Q4 will be on. Okay, this is short circuit, and here, so that means here there is no path to VDD. Why? Because open circuit. Okay, so here there is like so as there is no path, so what happens? You are getting like ground only. Okay, you are getting like a ground only. So that means
On.
there is no path. So the output is what? 0. Output is 0. Okay, and if it is 1 0, so Q1 will be off and Q2 will be on. Okay, and Q3 will be on and the Q4 will be off. Okay, so you can draw the circuit and analyze how it is, what is the output you are getting. Okay, so this will be off, this will be off, and
On.
this will be on. Okay,
On.
and next this is parallel.
Q3.
Yeah,
On.
Q3 is short circuit, and Q4 is open
Open.
circuit, and this is connected to ground. So there is a no path between VDD and output. So output equal to ground only. You are getting 0 only.
0.
0. Understood? Okay. And next at 1 1 what happens? Both are off state only. Both are off state, and Q3 Q4 are on state. Okay. So what happens? This is VDD, and so here both are off, open circuit. This is open circuit. Okay, open circuit, and these two are short circuit. These two are short circuit. Okay, so these two are short circuit. You are taking the output from here. So there is a mono path. So that means this is ground only.
From
You are getting 0.
it.
Okay, do you understood how I am doing?
Yes, sir.
Okay, can you do NAND as a task? Your task is you need to verify for NAND gate.
Nine.
NAND gate. No need to tell now. You can do for yourself. Yes, no?
Yes, sir.
NAND gate
Yes,
means
sir.
what? Just vice versa. Means what? For AND operation, what happens? This will be parallel and this will be series,
Please.
no? PMOS will be parallel. Previously I told for R operation, what will be there for R operation? So here you see. Yes. So for AND operation, PMOS will be parallel and NMOS will be series. For this one we did. Means what NOR gate we did. PMOS will be series, NMOS will be parallel. For NAND operation, how it will look like? So the expression is nothing but A and B whole bar, no? A and B whole bar. This is nothing but a PMOS will be parallel and NMOS will be series. Same like this, you need to draw the truth table and you need to draw the logic diagram, and you need to draw this truth table, and you need to see the cases when the PMOS will be off and PMOS will be on, and 4 cases you will get the circuit. Understood? Will you do now?
Yes, sir.
Okay. Next, the task is you need to design the NAND gate, and just show me, share the screenshot in the group. Okay. So this is y equal to what? A and B. Okay. Today itself you do, and just share that. And next is you need to design the Boolean equation using the CMOS transistor. How you design the Boolean equation using the CMOS transistor? Okay. So Boolean equation using CMOS transistor. CMOS transistor. Okay. So Boolean equation, let us take implement this Boolean equation. So my Boolean equation is y equal to A and B or C, A and B or C plus CD using CMOS transistor. Okay, CMOS transistor. How to design this Boolean equation by using CMOS transistor? Okay, so you already know. So that means for AND operation, which one will be series and which one will be parallel? NMOS will be series and PMOS will be parallel. Okay, and next for R operation, NMOS will be parallel, and PMOS will be series. Okay, so based on this I can draw the diagram. Okay, so first so my expression is, so once again I am writing. So y equal to what? Y equal to A and B or C or CD. Okay, so or CD. So based on this I need to draw this circuit. Okay, so first what is this? First we this is let us take this line is what? VDD. Okay, so A and operation is there. If it is AND operation, PMOS will be what? So PMOS will be parallel. Okay, R operation means PMOS will be series, no? So like here if you see, So this is what A. Okay, A. So A with AND operation. AND operation means what? So with A, B and C are parallel. Okay, B or C is nothing but OR operation. So that means B or C are nothing but a series. B or C are nothing but series. Okay, so B or C are series. Okay, and so this is what this is A, and next this one is B, and this one is C. This one is C. Okay, and again or means what? PMOS will be series. C and D. C and D means what? C and D are in parallel. So this series with C and D. C and D is parallel. C and D is parallel. Okay, so this is a PMOS. Okay, so this is C and this one is D. Okay, so this one is completed. Okay, and next, so here so again you need to come with the NMOS. Okay, so you need to come with NMOS. Okay, so if you see the NMOS, yeah, NMOS, if you see the NMOS, yeah, so I am drawing this NMOS. So here my expression is what? A and B or C plus CD. Okay, so for NMOS, so what happens for NMOS? So, so CD means what? C and D. C and D, if it is AND operation, NMOS will be series. Okay, so let us take here you see, so this is CD. Let us take first CD is, both are in series, this is NMOS, no, this is NMOS. Okay, this is NMOS, no bubble. Okay, so NMOS, this one is C and this one is D. Okay, CD and A and BRC. Okay, A and BRC. So when it is R operation, BRC is nothing but both are in parallel. Okay, so BRC, this is B and this one is C. BRC. Okay, so this one is B and this one is C, and both will be what? AND operation with A. Okay, so that means this is series. Okay, so this is series and next so this is A, and again here so you got all the expressions A and BRC plus CD. Okay, these all are connected with what? Ground. Okay, these all are connected to ground. Okay, all are connected to ground. Okay, now so that means you need to implement what? Complement. That means A or B whole bar you implemented directly. Here what? A and B whole complement you implemented, but here in the Boolean expression you here no complement is given. Okay, so that means here this one from the De Morgan's law I can write as what? Complement of complement is equal to what? True form. Okay, so that means this implementation is whole thing. Okay, again complement is there, so complement is there means again you need to implement with one more inverter. Okay, you need to implement with one more inverter. Here I am implementing, so that means here you will get this is PMOS, and next one second, this is PMOS, and this is NMOS, this is NMOS. So this is PMOS and NMOS. This is one more inverter and designing. So here this one is connected to this input. Okay, you are taking the output from here. Okay, so this is Y. So what is my Y? Y equal to A and BRC plus CD. Did you understood how I am implementing?
So can you explain this diagram once again?
Which one?
Diagram.
Diagram you are asking?
This diagram. Yes.
This diagram. Okay. You see here, suppose we already seen, no. So for AND operation, so this is AND operation. Okay, for AND operation, so NMOS will be what? Series, PMOS will
Yes.
be parallel. PMOS will be parallel. Okay, and for R operation, okay, which one will be series? NMOS will be parallel.
Mm.
NMOS will be parallel. Okay,
Parallel.
parallel, and PMOS will be
Three.
series. PMOS will be series. Okay, now you see. So related to the PMOS, so this is nothing but what? This is nothing but this is BRC, no?
Piece.
BRC. Why? Because R operation, PMOS will be series, no? Okay,
Yes.
this whole thing, so that means this and this we can write as what? A and B R C. Why? Because if it is AND operation, both are in parallel, no? PMOS, this whole thing is nothing but A and B R C. Understood? Okay, and
Yes.
next for AND operation, this PMOS will be what? Parallel, no? So this is nothing but C and D. This is nothing but C and D. Okay, this is nothing but R operation. R operation means what? This one, and this one. Okay, this one will be what? Series. Okay, series. So this is series means this whole thing you will get what? A and B or C plus C plus or CD. Do you got PMOS implementation? Did you understood?
Yes.
Based on
Yes.
this only I am writing. See here. For NMOS you see. So NMOS C and D. So for AND operation, NMOS is in series. Okay. So this one is C and D. Okay. And next this one you see. So this one BRC. So BRC means what? NMOS in parallel. So this is BRC. And AND operation. NMOS will be NMOS will be series. So A and BRC. Okay, and whole thing is nothing but R, no? R means what? So R means you can write A and B or C or C D. Okay, but here my expression here you given in a true form. Okay, so CMOS when we will implement it means we implement it directly for NOR gate and NAND gate. That means this is complemented form. It is given, we can implement. Okay, so but how to implement this? That means we know that from De Morgan's law, A bar whole bar or inverter law, A bar whole bar equal to what? A, no? So
Yes, sir.
this one A bar whole bar. So uh, this one I implemented. Which one? This is nothing but this circuit. Again inverter is there, no? So this inverter I need to implement. Okay, one more inverter, you will get this function. Did you understood? Shall I? Any doubt?
Yes.
Okay, shall I move forward? So like this, you
Yes, sir.
can find out any Boolean expressions, and you can implement any Boolean functions also. Okay. So like in digital, we implemented one function. No, what is that function? We implemented by using NAND gate and NOR gate. You can go through the digital circuit, and you can implement that functions also. That let us take y equal to a bar plus bc bar we implemented, no? Okay, so this you can implement. Okay, this is task 2. This you can implement using CMOS circuit. Okay, and one more logic circuit I given. Okay, so logic circuit you will get the expression. That circuit, that logic circuit you implement using CMOS circuit. CMOS circuit. Is it fine?
Yes, sir.
Okay.
Yes, sir.
Next, CMOS multiplexer. CMOS multiplexer. How to implement this CMOS multiplexer? So we done with the basic universal gates, NAND gate and NOR gate, and next we have seen the Boolean expression, and next you need to implement CMOS combinational circuit, that is nothing but multiplexer, mux. Okay, so multiplexer. So here we will take the simple multiplexer, that is 2 cross 1 mux. 2 cross 1 mux. Okay, so 2 cross 1 mux means you know the functionality, no? So what is 2 cross 1 mux? In digital we already seen. This is 2 cross 1 mux. 2 cross 1 mux. So how many inputs and how many outputs?
2 input, 1 output.
One second. One second. Hello. Good evening, man. చెప్పండి. ల్యాప్టాప్లో అది టూల్ జిప్ ఫైల్ చేశాను కదా, జిప్ చేశాను కదా. అన్జిప్ చేయాలి. మీ దగ్గర విన్జిప్ అవన్నీ ఉంటాయి కదా ఇన్బిల్ట్. నేను జిప్ ఫైల్ పంపించాను, జిప్ చేసి పంపించాను, మీరు అన్జిప్ చేయాలి దానిలో. అన్జిప్ డివి కోర్, అవును. ఓకే. ఓకే. ఎక్కడ కంప్లీట్ చేసిన టాపిక్స్? నాకు అర్థం అవ్వలేదు నేను చెప్పింది. అవునవును. ఓకే. సరే చెప్తాను. ఓకే. కవర్ ఇచ్చావు లిస్ట్. ఓకే. సరే. ఓకే. Yeah, 2 cross 1 mux you can do, no? See here, 2 cross 1 mux. What are the inputs? I0, I1, and output. What is the output? Y. And what is the selection line? Yes. Okay. Selection line. Output Y. So 0, 1 and 1. If it is 0, selection line is 0, I0 is connected. Selection line is 1, I1 is connected. Okay, what is Shannon's equation? Y equal to S bar I0 plus S I1. I1. Okay, S bar I1, S I1. Okay, so here I can implement. Okay, so that means for AND operation, NMOS will be series, and PMOS will be parallel. Okay, parallel. And for OR operation, NMOS will be parallel, and PMOS will be series. PMOS will be series. Okay, so based on this you can implement, no? So you can implement this circuit. Okay, so Y equal to S bar. So I am implementing this. So that means this is a Boolean equation only. Y equal to what? S bar I0 plus S I1. Okay, so this is VDD, and next S bar I0 means AND operation. PMOS will be what? Parallel, no? PMOS will be parallel. Okay, parallel. So parallel, and so this is PMOS. So this is S bar I0, Again, OR operation means what? Series, no? So series. So this is series. This is OR operation. Okay. This OR operation you will get. Okay. OR operation. So this is AND operation. Okay. And this is OR operation. Again, AND operation means what? Parallel. AND operation means parallel. Okay. This is parallel. Okay. So I1. I1. Okay. So again this is AND operation. Again, pull down network. Okay, what is pull down network? So here uh, this, so S bar I naught. Okay, for AND operation series, for AND operation this is series, for OR operation this is also series. Okay, for AND operation this is series. Okay, again OR operation means parallel. Okay, so this is OR operation, these two are AND operation. Okay, so NMOS, S bar I naught and S I1, S I1, and this is connected to anyway ground. Okay, this is connected to ground. This is connected to ground. Okay, and here you need to take output from here, but my expression is what? Normal logic expression. This is what? S bar I naught plus S I1. Okay, so that means A bar whole bar equal to what? A only, no? So complement of complement I am writing. Okay, so that means this is this one is nothing but what? This one I implemented this circuit, okay. So one more complement is there. So one more complement means what? So this is connected with one more inverter. This is PMOS, and this is NMOS connected together, and here this is ground, and this is VDD. Simple, no? Did you understand?
Yes, sir.
Okay.
Yes, sir.
Yeah. So task 3 is you need to implement. So task 3, you need to implement half adder using CMOS. Half adder using CMOS. Okay. Half adder means what? What is sum? For half adder we already discussed. No, sum equal to what? Tell me. For half adder in digital we already seen, no? Sum equal to what? A XOR B, no? Sum equal to A XOR B. Okay. So this is equal to what? A bar B plus AB bar. Okay. So this AB bar, this I can write as what? A B plus A bar B bar whole bar. Can I write? A bar B bar whole bar. Okay. So XOR gate I am writing like this. A XNOR B whole bar I am writing. A XNOR B whole bar I am writing. Okay. And carry equal to what? Carry equal to AB. Carry equal to AB. So this I can write as what? AB whole bar. Okay. So this if you apply De Morgan's law, what you will get? A bar plus B bar whole bar. Okay. Separately you need to implement for sum by using CMOS, and separately you need to implement for carry. Is it fine now? Give response.
Yes, sir.
Yes, sir.
You can do, no?
Ye-
Okay, you can do
Yes,
for
sir.
CMOS half adder. Okay.
Sir.
Tomorrow we'll see the sequential circuits: SR latch, SR flip flop, okay, D latch, okay, and JK flip flop. How to implement by using the CMOS circuits. Okay. So 3 tasks you need to complete, and you need to come with solutions and any doubts or any queries. Okay.
Sir, once can you Second task question.
Second task, second task. Second task, y equal to a bar plus bc bar. You need to implement by using this Boolean expression. You need to implement by using CMOS circuit.
Okay, sir.
And during the NAND realization and NOR realization in the digital, I showed one circuit, no logic circuit. Just to go through that digital, that logic circuit, in that logic circuit, you get the Boolean equation. That Boolean equation you need to implement by using CMOS circuit. Just to go through the digital in the digital I told you when I explained the realization of Boolean expressions by using only NAND gates and NOR gates. I took two examples. This is first example, and second example one more logic diagram I took, and I explained the realization. Okay, there you need to get the expression and implement by using CMOS circuit. Yes, any doubt or any query?
Sir, now second one you told logic gate of NAND only, no?
No, that is a combinational circuit. Actually, you go through that my lecture series on the digital. I gave one logic circuit in the realization of this one. Okay, one second. Okay, okay. Okay, so you in that you go through that logic circuit and get the logic expression. Okay, if you want. Okay. Okay. Just to go through that. Any doubt means we will discuss tomorrow. Okay.
Okay, sir. Like, what is that logic circuit picture? Anything you have, sir? Like,
One
so
second.
many we discussed, no. Which one we don't know.
One second.